Hello friends, Assalamu alaikum. Welcome back for another interesting video. Now moving on from the multilayer networks like the multilayer perceptrons to deep learning. So we are going to talk about origins of deep learning in this video. Technically, when the term deep learning first occurred, when it was first used, what people referred to it was the representation learning when with advanced architectures with many layers. So having multiple layers is not really what makes the difference between a multi-layer perceptron and deep learning. It's more like the representation learning capabilities. That is usually what deep learning is all about. Nowadays though, if you read papers where people use multi-layer perceptrons, they call them deep learning too. So I think nowadays it's okay to call it deep learning to make it maybe less confusing for people because everything nowadays that is a neural network is also automatically deep learning. But let's dive a little bit more into the representation learning aspects that I just mentioned. So that goes back to approximately 1990s. Also in that way, it's a thing that was discovered or invented before deep learning was a thing. The word deep learning, and it is convolutional neural networks. So this is kind of on top of the multi-layer perceptrons. It's like you can think of it as a specialized version where you have locality. So here it's about making training more efficient and also extracting local features which then better capture feature dependency. So recall in multi-layer perceptrons we had like feature independence, so it would work with tabular data. Now with this convolutional network we can leverage some prior knowledge of this relational inductive bias. So it's specifically for image recognition for image data. So how multi-layer perceptron works is that you have these independent features and then convolutional network captures this dependency. On the right hand side, I'm showing you this original Linux architecture from Jan LeCun and co-workers that was applied to handwritten zip code recognition. And we will have a dedicated lecture just to convolutional networks later. But here, just a brief overview of uh, is that it consists of two parts. So there's one part that is convolutional part. So here you have convolutional layers. They have a trick or concept called weight sharing, and there is also pooling involved, and that makes the training more efficient. We will discuss this in more detail later, but you can think of it roughly as the feature learning layers, where these layers are able to extract features from the data, and these features are then passed to the fully connected set of layers. So these are the fully connected layers, and these are essentially multi-layer perceptrons, and you can think of it as a classifier here. If you think of it as a task, here we have this part, the lower part here for feature learning. This upper part is for classifying the features that have been extracted by these earlier layers. So this is making the handcrafting of the features obsolete. Now the network learns the features, and it learns in such a way that it is optimal for the classifier, because everything here is connected. So it's learning together, which is one advantage that makes neural networks for image data specifically very efficient. So this is again from the 90s. Back then the term deep learning didn't exist, but I would say nowadays convolutional neural networks are really like the most popular form of deep learning, because there are many advances that followed these earlier architectures and made deep learning what it is nowadays. Of course, there's also a separate branch of recurrent neural networks that is also very popular in deep learning. So recurrent neural networks are also, I would say, an advanced version of the multi-layer perceptron. So here what's new is that there is a recurrence. So you can think of this as a multi-layer perceptron, but a multi-layer perceptron is a feed-forward network. Now you have this recurrence, so you are revisiting earlier things. So again, this will be covered in more detail in dedicated lecture later, but the key idea is basically that we have a modified version of back propagation, which is called back propagation through time, because there is a time component involved. And this is especially useful for sequence data, where there's a sequential dependency in the data across the features. But the problem with that is now when we train this neural network with many layers, especially for recurrence over long sequence, there is this problem of vanishing and exploding gradients. So that is like a big challenge. However, there are many potential solutions to that. And one of them that is still commonly used is LSTMs, that stands for long short-term memory. Also, this one was like overcome, and this is also one popular form of deep learning using these neural networks. But again, this is something that has been around for a long time. I don't know exactly when recurrent networks were invented. First, it was like also in the 1980s, uh, sometime after backpropagation was invented, because this is an advancement of backpropagation. Now, going from these architectures I showed you that were invented in the 90s towards the modern era of deep learning research, there was unfortunately in between another AI winter in the later 1990s and early 2000s. And I think that was probably due to the popularity of support vector machines and random forests, because back then neural networks were capable, but they were very expensive to train. So you needed like enormous computer hardware to train them efficiently, and even then you had to wait a long time to train them, so they were not easy to train compared to, let's say, support vector machines and random forests. Of course, support vector machines came with their own set of problems, like the inefficiency of RBF kernel machines on high dimensional data. Also, random forests require a lot of trees, but still compared to deep neural networks, these were easier to train and worked quite well. So, but then at some point, people figured out how to use GPUs to make the training of neural networks more efficient. So when I looked at literature, what I could find, it goes already back to 2004. So on GPU, implementation of neural networks have been around for quite some time. But really, when it became popular was in 2012, where Khrushchevsky, Suitskever, and Hinton worked on ImageNet classification. So very common benchmark dataset, like millions of images, where they used deep neural networks trained on GPUs to outperform traditional computer vision approaches. So here's the table. So bottom line here is more the difference between traditional CPUs, for example here an Intel CPU and an NVIDIA graphics card, or in general a graphics card. Well, maybe think of it as a difference between a CPU and a GPU. And GPUs are particularly good at linear algebra operations like vector and matrix operations. So even though GPUs have a smaller clock frequency, one advantage is really like the parallel cores. Each column is slower than a CPU core, of course, but you have more of them, and that helps you parallelizing computation. So parallel computing of dot products and matrix multiplication is really what makes GPUs very useful for deep learning. So you really get a way higher memory bandwidth. So the GPU memory, and CPUs come with their own memory. GPUs come with their own memory, which is closer to where things are computed. So it's also faster in that way. If you have the data on the GPU, however, you have to get the data on the GPU, which is sometimes a little bit slower. So there are some tricks also to make this efficient in terms of data loading. So really, you can see the number of floating point calculations. A float is, you can think of it as a decimal number in the computer. You can see it it has a way higher number of floating point calculations, and it's also cheaper, at least compared to this high-end Intel CPU. But of course, there are also things with GPUs that make certain things inconvenient, because they have their own memory, which is not very large. I mean, there are nowadays more expensive cars that have larger memory, but usually in deep learning, GPU's memory is bottleneck, at least for me. But again, that is a topic for another day. And here's also just a quick overview of the benchmark datasets. Nowadays, there are others, even bigger datasets, but these are still common datasets when you develop convolutional networks or object classification methods. So there is this traditional MNIST dataset from 1998, 60,000 examples, 10 classes, and very low resolution images. So these are handwritten digits. So this is still a great dataset for debugging your network. It's like when you want to try a network get the code written and see whether it works, because it's really fast to train a network on that. In practice, if you write a conference paper, testing your method on this MNIST may not be enough anymore, but it's still a good way to start more. I would say advanced dataset is Cipher 10 and Cipher 100. So there are 60,000 examples of either 10 classes, which is for Cipher 10, and 100 classes, which is for Cipher 100. Again, very low resolution, 32 by 32. Now that we have color images, so we have 3 color channels, and we have different objects here to classify this. Usually only one object in each image. A more challenging dataset is the ImageNet dataset, which consists of 14 million images. So they have full resolution, and what is a little bit more challenging about that is that there can be multiple objects in an image. So what can happen is that there could be multiple objects sometimes, so it can be kind of ambiguous. Usually what people do is measure the top 5 accuracy or error. For example, when you have a prediction, you check whether your top 5 labels are matching with the image label, because the network is trained to return the probability or confidence score for each possible class. And then you look at the top 5 most confidence labels, and you look whether one of the 5 labels matches with the labels in the image. So here, for example, we have actually also 2 things. We have a cherry and a dog. So it's also, you can see this image is a challenging example where your network may predict a dog, but since the data point here is labeled with cherry, it would actually count as an error, which is unfortunate. So you would look whether your prediction is kind of within top 5. Or here in this case, your algorithm may predict car or grill, like a grill of a car, but both would be correct. So in that way, you look whether a grill is under your top 5, for example. So in that way, it's a little bit harder to evaluate on the ImageNet compared to Cipher 10. I think in Cipher 10 it's a little bit more obvious, but here you have classes where it's at least a little bit less ambiguous. Now moving on, so the last thing here, of course, there have been many advances in 2012. Since 2010, for example, advances that are making deep neural networks work way better. So common ones are popular ones like ReLU units, rectified linear units, which are activation functions, very simple but very effective. Batch normalization, dropout, generative adversarial networks, and these all shall be covered, and many more. So there have been a lot of advances also in the last decade, and also there are way more of these, and they are all contributing together to make deep learning work better.